Start the recording. Right. Okay. So welcome everyone to the quantum assignments program quantum seminar. So today we're happy to have Anurag Anshu give the talk. So Anurag got his PhD with Rahul Jain in CQT in Singapore, and he's now a postdoc at the IQC in Waterloo. And he's going to tell us about some exciting work with Itai Arad and David Gossett on some improvements to the area law for higher dimensional Hamiltonian systems. Yeah, please feel free to interrupt with questions at any time. And Anurag, cheers. Thanks.
Yeah, thanks, Thomas, for the introduction. By the way, I hope all of you are doing well. And let's stay strong, and we'll all get through this. I meant about the talk, but also coronavirus first. Okay, so this talk is going to be a work with Itai Arad at Technion and David Gossett here in Waterloo. The talk is divided into 5 sections. I will pause at the end of each section. You can ask me questions right there. You can also interrupt in between. So yeah, let's get started. So here on the screen, it's a standard system of interacting particles. So it could be a collection of electrons or something like that on lattice structure. What I've gathered from much of literature is that these systems are very important for physicists. It turns out that their properties are something which have some novel features. So for instance, there's a material called graphene, which happens to have very exciting electronic properties. So physicists are really interested in this study of these systems, and in fact, they would like to simulate these things. Now, for convenience, I'm going to simplify the structure of the lattice. It was a complicated hexagonal lattice here, but for the sake of easy drawing on pig's picture, I'm just going to make it a square lattice here. And I will assume a simple kind of interaction without loss of generality for the talk. It's all for convenience. So I'll assume that the blue dots on the screen, which are supposedly the particles or qubits, they interact locally. For instance, here, these 4 qubits interact using an interaction H. A standard practice is to choose some normalization. I'm going to assume that each of this small h is a bounded operator between 0 and identity. So which means that the energy of each local interaction is not too large. I mean, it's a reasonable constant. Now I can take the collection of all the interaction, and I can write down a Hamiltonian, which is also called a local Hamiltonian of the system. So here the local Hamiltonian would be a sum over all the colored squares or plackets, which I have summed this way, and each of Hij only acts on spins I plus 1, Jj plus 1 on these 4 spins. I'm going to label the x direction, the horizontal direction from 1 to n minus 1, 1 to n, and the vertical direction from 1 to L. And so this is the full interaction. Now, by the way, I forgot to mention, you will see that the color of the title changes from blue to orange to red. And what it means is that if it's a blue title, just think of it as a very simple slide. If it's an orange one, it's going to be mildly technical. If it gets red, it's going to be quite technical. So you know when to switch the tab and go to watch YouTube videos and stuff. All right. So here's a mildly technical slide, for example. I'm going to label the ground state by this notation, ket omega. It's the eigenstate with, ground state is an eigenstate of the Hamiltonian with the smallest possible energy. We're going to assume for this talk that it's unique. The spectral gap, which I'll denote by gamma, is the difference between the smallest and second smallest eigenenergies. This talk is going to be about frustration-free systems. What this means is that each of the interaction Hij, when it acts on the ground state, it gives a 0, which means the ground state satisfies all the interactions. So so it's frustration-free. None of the local terms are frustrated. And it turns out that this is something that will be useful for the talk and I will get to this point later as well towards the end. If your Hamiltonian is frustration free, then you can do a simple transformation. That is, you can take your local interaction Hij and you can replace it by a projector onto the span of this Hij. It turns out that it does not change the ground state because the ground state continues to be the ground state of the span as well. It changes the gap by a constant that may depend on the details of Hij. It may depend on the second non-zero eigenvalues of this Hij, but we are assuming those things are constants. So from now, I'm going to assume a frustration-free Hamiltonian in which each of the local interaction H is a projector. And I will take the spectral gap to be gamma, and the ground state will be a unique ground state that's at omega. All right, so we'll talk about entanglement and entropy in this talk. So here's a slide on that. Imagine that I divide my collection of particles into two regions. One we call A, one is A complement. A is on the left, A complement on the right. And the orange line is the boundary, which I'll denote by partial of A. I'll just call it boundary of A. So the question is, what is the entanglement entropy of the reduced state of the full ground state in the region A? So there are three things which people usually refer to colloquially. First thing is known as an area law behavior, which states that the entanglement entropy or the entropy of omega on the region A scales as the boundary of this region. A trivial statement would be a volume law, which says that the entropy scales as boundary square. That might be, I think that might be a bit confusing here because it's not clear whether this also is boundary, but assume that this dimension and this dimension are quite similar to each other. So by simple isoparametric inequality or something, just by square of the length, trivially the entropy is at most the number of particles in the region A, and that scales as the boundary square. A subvolume law behavior would be when the entropy scales as length of boundary to the power some constant C, where C is strictly between 1 and 2. So that is an intermediate feature. A very well-known conjecture is the area law conjecture, which says that the ground states of gapped Hamiltonians, which means I'm going to take the gap gamma to be a constant, they satisfy an area law across every reasonable bipartition of the lattice. So here is one reasonable bipartition. You could also draw a rectangle here, a triangle here, things like that. So that is the area law conjecture, and usually conjecture is referred in the context of unique ground states, but it's not always necessary. Also for non-unique ground states, people have made statements about this. So why is this conjecture interesting? Well, one reason is that if you take a random quantum state on these particles, they satisfy a volume law by a simple counting argument. So if your ground state satisfies an area or subvolume behavior, then this means that the ground states are somehow simpler than most quantum states, and there is a hope to be able to study them with lesser complexity than you would have if you had no such information. All right, so let me quickly go through what is known about this conjecture. In one dimension, the conjecture has been very well studied, starting from the breakthrough work by Hastings in 2007, who showed a bound of the form exponential in 1 over the gap. So think of a one-dimensional system as the one shown in the picture here. And if you divide this collection of particles into any two parts, Hastings showed that the entanglement entropy in any region scales in this way. For frustration-free systems, which I think I didn't mention this earlier, but I'm going to abbreviate it as FF. For frustration-free systems, Aronov, Arad, Landau, and Vazrani, they showed using a different technique, scaling of the form, a similar scaling, which Arad, Landau, and Vazrani later improved it to polynomial in the 1 over the gap, and then later it was improved to 1 over the gap for any system. There's an interesting conjecture of David and Yichen from 2016, which proposes that the scaling for the frustration-free systems should be 1 over square root of the gap instead of 1 over gap. So this statement is true for any system, any frustrated or frustration-free system. But they pose this conjecture, and the motivation behind this is that they prove that the correlation length, if you're aware of what it is, I will not talk about it anymore apart from now. That the correlation length in frustration-free systems scales as 1 over square root of the gap. And the heuristic or the intuition behind area law is that entropy should scale as the correlation length. And that's why they have this conjecture. This conjecture will feature in the last slide again. So there's nothing to think about it for coming 29 slides. All right. This set of results have been very useful, especially in the context of representing one-dimensional ground states in an efficient manner, which can be used for simulation or computation of interesting quantities. So for instance, 1D area law or some variation on it implies that the gap ground states can be approximated by a matrix product state, which is a state that looks like this in the picture, of small bond dimension, which means the number of parameters required to describe it as small. And it supports the success of the very well-known DMRG algorithm. In fact, the tools that have been developed for in these papers for area law have been very useful for giving provably polynomial time algorithms for ground states. All right. Since this talk is about 2D, let me mention what is known in 2 dimensions. Under several assumptions, the area law has been shown for ground states of local Hamiltonians. One assumption is that you have small number of low energy eigenstates, which is a reasonable assumption in many cases. If you have the system of qubits, which is spin half with nearest neighbor interaction, even in this case, an area law behavior is known under some adiabatic assumption and also under assumptions on specific heat. It turns out that if your Hamiltonian is commuting, which means that each interaction mutually commutes, then it's easy to show, of course, easy is a relative term, but with some knowledge about this area, you can show that area law holds in all dimensions, not just 2D or 3D, in fact, all finite dimensional lattices. All right, so I'm going to pause here for a moment. Any questions so far about any of the results or any comments? All right. So I'm going to spend one section on describing the tools that are available for bounding the entanglement entropy. For this, I will need a notion of Schmidt rank of an operator. If you recall the partitions A and A complement of the 2-dimensional lattice, an operator K is said to have a Schmidt rank D if it can be decomposed as a linear combination of product of 2 operators, where Ka lives only on the A region, which is the left region, and A complement only lives on the right A complement region. And throughout this talk, we're going to denote it in short by SR of K, or the Schmidt rank of K. Now, let's see what would be the most intuitive way to try to prove an area law. It would be that, let's say there was a operator, a PSG operator, positive sum definite operator. Let's call it K imaginary because turns out it doesn't really exist. Such that this operator was very close to the ground state in L1 norm, up to a very small letter epsilon. And also imagine that the Schmidt rank of this operator was also very tiny. Then you can use a simple Alecki-Fans inequality and say that since the information in this K imaginary between A and A complement is very small, at most log of this small value, it turns out that up to this tiny error, even the ground state would satisfy a good upper bound on the entropy. So this could be one way to try building up such operators and proving the theorem. But turns out that these operators don't exist. And one has to make a living with a weaker condition, which is that you can only find operators K which are close to the ground state in infinity norm for a reasonable epsilon. Of course, I'm just being a bit vague here. One has to be precise about what is epsilon and what is small and so on. But for all practical purpose, it turns out that these operators, which are approximating the ground state in L1 norm, are very hard to get.
Anurag?
Yep.
Can I ask a question? So in the third bullet in the middle, where does the I see the epsilon? No, I was going to ask where does the size of A? How come the size of A comes? Because the assumptions don't involve the size of A, but this is some inequality that you use there.
Yeah. A is the number of particles in the whole region. it's just a it's just using Elie-Kefen's inequality. You could prove something like this, but
Okay.
Just think of it, if the information here is small, then information here is small too, sort of. And just this slide is very colloquial. Oh, sorry, it should have been a blue slide, I believe. Anyway, so the true situation is that you only get an approximation to the ground state in infinity norm. For example, think of e to the power minus beta h, which is something you think of. It approximates the ground state only in infinity norm. And one has to make a living with something like this. And indeed, in this series of works, a lot of tools were developed to tackle this notion of approximation. And this is the approximation. This is the idea of approximation to the ground space. So we start with an operator k, which approximates the ground state in infinity norm. I'm going to denote the approximation by the symbol delta. I will call this shrinking factor from these works. And the Schmidt rank of this operator k is d. It turns out that for frustration-free systems, we also have an additional guarantee that k keeps the ground state unchanged, which means that ground state is a +1 eigenstate of this operator k. I'm going to describe in a few slides how does it look like, but think of an operator k which might exist of this kind, and then let's see what can be shown about this. So a theorem which I'm quoting from Arut Landau and Vasrani, but it appeared in some form in Hastings' work in 2007. It says that the entropy of the ground state is upper bounded by the following quantity, where if you recall, d is the Schmidt rank of the operator k, delta is the closeness or shrinking factor. So entropy is at most log d by log 1 of delta times the min entropy of the ground state in the region, which is min entropy is simply log 1 over the largest eigenvalue of this state, which also is very closely related to the closest product state that approximates the ground state, and plus this factor of log d. This lower one is obvious from basic information theoretic inequalities, and this is a very fundamental relation that has been known from prior works. So what can you do with this relation? So one way is to find a nice k which has a small d and a small delta, and to prove that the min entropy is small as well. That's one approach that was taken by Hastings. And the second approach is to observe is that if this factor is small, then you can do a kind of bootstrapping in this equation. And that's observation. That's an important observation from this work, which I will use in the rest of the talk almost entirely, is that if a relation like this holds, or more precisely quoting from these authors, if d and delta is less than half, which we'll refer to as the AGSP condition, then what happens is that you can use this relation to say that the min entropy is small, and then you use it again to say that the entropy must be small too. And that shows that the entropy should be at most constant times log d. So I hope this slide is pretty clear. I mean, I won't go into describing this thing. You should refer to this work for that. But this is the upshot of this line of argument, that you find an operator k whose Schmidt rank is d, shrinking is delta, and they are relatively, d and delta is less than half, and then you get a guarantee on the entropy or the entanglement entropy of the ground state. All right. So these works also observed that it's a nice idea to construct the AGSPK as a polynomial of the Hamiltonian. So just to give an idea of how does that work, you can think of the ground state as a function of a Hamiltonian. So define a function f ground, which takes a value 1 whenever the input x is 0, and it takes a value 0 otherwise. So if you just feed in the Hamiltonian to this function, you will, what comes out will be the ground state, and then you can think about approximating this function using tools from approximation theory. So here's a slide which explains how would you use a polynomial of the Hamiltonian and try to satisfy the AGSP condition. And here's how it goes. So imagine that this polynomial k of h has a degree d. So what's the utility of having a polynomial? It's the following: that you expect that if your operator is a polynomial, then its Schmidt rank should be small. It should be something like exponential in d. Let's get an intuition for that. So expand your polynomial of the Hamiltonian and look at a multinomial, for instance, h7, h7, 3, and so on. And let's say these terms come d times. That's a degree. And also notice that these operators act on a vertical direction, which lets the partition is between 1 to 7, then 8 to n. So because these terms appear d times, each of them would increase the Schmidt rank, would have a Schmidt rank constant, and d of them would have Schmidt rank e to the power the degree. So from this you can kind of infer roughly that the Schmidt rank of a polynomial of degree d should scale as exponential in the degree. And you already have some guarantee delta on the shrinking parameter, that's e to the power minus s. And then you want to use these two parameters and try to prove a theorem. So you would need that d is less than delta, less than 1 over delta, which kind of translates to saying that the degree should be less than the parameter s here. So if this was true, then you would have this property that the AGSP condition would be satisfied and you would have some bound on the entropy. But turns out that from the study of polynomials, it's very hard to satisfy this condition as it is. So one has to develop more tools, and this was already done by these authors. And this is going to be a technical slide, so I'll go fairly slowly here. And the way to satisfy the AGSP condition using polynomials goes in this way. You look at your lattice, you look at your cut, which is the orange line over here, and you choose a certain region of the lattice which is close to the cut. So here I'm picking up T columns around the cut, around the bipartition, and I'm totally ignoring everything beyond it. All the light blue particles will be totally ignored. And boundary is just this length. So the idea is to construct a family of AGSPs, which are polynomials of the Hamiltonian, which will be KT. These AGSPs will be a degree dt polynomial, which a degree d, which I am labeled with d, with t, polynomial in the dark blue region. By the way, apologies for choosing d and t in the slide, and in the future slides, it's a bit confusing, I guess. Whenever there's a confusion, I'll say t for tomato or something, just to make it clear. So I'm going to take a polynomial degree d sub t in the dark blue region and let the shrinking be e to the power minus some function of s of t. Then the upshot of the theorem that was shown in this work and also in the later work is that if degree d as a function of t is at most t times the shrinking factor s of t, then the AGSP condition is satisfied and you obtain an area law of the entropy bound of the form t times the boundary length. There are a lot of assumptions that go here. For instance, these polynomials have to be of certain nice form. You can't take any arbitrary polynomial of the Hamiltonian. But I will ignore those issues. So philosophically, you can think of it as instead of this stringent condition that d should be less than this parameter s, you get a relaxed condition that d should be less than a fairly big number that you can choose times s. So you just make sure this condition is satisfied, and then you get a bound on the entropy. All right. So any questions so far? Given that polynomials have entered into the picture, I'll describe them in the upcoming section. But I'll pause for questions if there are any. If there is any confusion about this theorem that I mentioned. Or if I'm going too fast, then you can tell me. I'll probably slow down. All right. Okay, so let me go into discussions about polynomials, especially the polynomials that these works considered. So here's our f ground back, which is the function that when input the Hamiltonian spits out the ground state. So here's my function, and I have denoted it by this blue line over here. It's not very continuous, unfortunately. It turns out that you can approximate this function under some guarantees using Chebyshev polynomials, and they do the following. The Chebyshev polynomial is going to approximate the function. So the Chebyshev polynomial is this green line over here. It's going to be close to the function value at point 0. It might take some values here, but because we are interested in the Hamiltonian, from the point of gap gamma all the way to the region T times delta A, which is the blue region over here. I've totally ignored these spins. There's a lot of details here as well, which again, these words develop, but there are ways to get around not thinking about these regions, the light blue regions. So in the zone from a gap of the Hamiltonian all the way to the largest value, t times the boundary of A, this function stays small. So it's clear that this function approximates this f ground function in the region of interest, whatever region is given by the whatever energy scale is given by the Hamiltonian. And it turns out that these Chebyshev polynomials for a given degree are also the best polynomials you can hope for, which achieve this guarantee. So now from this slide to the 39th slide, I'm going to assume that gamma is a constant just to not keep it around. Think of gamma as 1 over 2, 1 over 3. So the gap is a constant. So you want the Chebyshev polynomial to approximate this function by staying very small in this vector from some constant all the way to this number. So let's look at
just one question.
Yeah.
Why is it enough to be small only up to t times the boundary? Why don't you need to go up to the norm of the Hamiltonian?
Right. So it turns out that, again, it follows from these works that you can write a new Hamiltonian which is only effective in this region. And its norm, the contribution to the norm from outside is very small. That's a bit of massaging one has to do. So yeah, for the coming all the slides, pretty much, let's assume that think of the Hamiltonian as only living in this region. For now, I mean, of course, it has to be made more precise, but yeah. So we'll think of it as going from the gap all the way to the effective, let's say effective norm, just look at minutes, to the effective norm, t times the boundary. All right. So let's try to see what guarantees we get with the Chebyshev polynomial. We get that the degree of this polynomial is square root of the norm, effective norm, that's t times the boundary, for a constant shrinking, that is if delta is 1/3. This is very analogous to what happens in Grover search, which can solve the AND function with root n queries. Just a clarification here that I'll switch between the range of the energies of the Hamiltonian and the AND function quite a bit, but they are equivalent due to what is known as the symmetrization method, which means that the function that Grover search creates for solving the AND, that is a symmetric function, and hence you can view it, it's symmetric polynomial, hence you can view it as a function of the polynomial of the Hamiltonian, which counts the Hamming weight of the string. All right. So Chebyshev polynomial gives us this guarantee that the degree is root of the effective norm, that's t times the boundary length, and delta is 1/3. Let's plug it into the condition that I mentioned earlier, that d is less than t times the boundary, t times the st. So if this is true, then I get a guarantee like this. So let's plug things in, and it turns out that if you just evaluate from here the value of t for which this condition is satisfied, then you find quite easily that t should be pretty large. T should be the length of the boundary itself. Now, when you plug it in here, then you just get a volume law, that is boundary is square. That's the guarantee on the entropy. So this is still the trivial one volume law. But the nice thing about this is that any improvement to the behavior of Chebyshev polynomial would give you a subvolume law, which is what we'll do. And this point was already observed in the previous works. But okay, so this is unfortunate that we still got a volume law behavior with a good polynomial like Chebyshev. But there's something seems very strange about this. What's strange is that this line of argument continues to give a volume law even for the commuting case, when all the terms are commuting. But I mentioned in one of the earlier slides that the commuting case already satisfies an area law. So what's going on? Is it a problem of the technique, or it's some? I mean, do you need to do something else for commuting Hamiltonian? Maybe this technique doesn't work for commuting Hamiltonians. And that's where it turns out that well, I mean, you can fix this issue for the commuting Hamiltonians. You can actually get an area law, but for that you have to look into a related family of Chebyshev approximations. And this comes from, I mean, the first place that I'm aware of the work is by Kahn, Lineal, and Samarodinsky. They showed that if you are interested in doing a Chebyshev approximation for integer points only, which means that instead of this slide where I was interested in the approximation all through this real interval. I'm only interested in the integer points. Then I can improve upon the guarantees that are given by Chebyshev. So let's see what happens. Let me remind, maybe I didn't mention it earlier, but commuting Hamiltonians, frustrated Hamiltonians turn out to have integer spectrum. Because if you remember, I assumed that the projectors, the Hamiltonians terms are all projectors. And they commute, so they all have integer spectrum from 1 to 0, 1, all the way to the t times the boundary, which is the effective norm. So what these authors showed is that approximation to the ground function, if you only are interested in the integer spectrum, is better than Chebyshev. And it so happens that the shrinking factor, that is e to the power minus this st, it turns out to have the following form, that is square of the degree divided by the effective norm, t times the boundary. And this holds for all the values of dt starting from square root of this number to the effective norm. And so it so happens that if dt is equal to this value, then this is just constant, which agrees with what Chebyshev guarantees. But if you take d to be higher, then you get improvement over Chebyshev. For people who like to think in terms of query complexity or in terms of quantum algorithms, then I'd like to point out that this polynomial also discovered independently by Burman, Cleve, Wolf, and Zalka in 1999, who showed that the quantum query complexity of AND function with error epsilon actually requires root over n log 1 over epsilon queries instead of this log 1 over epsilon outside. And this difference is precisely what is captured by these polynomials. And just think of log 1 over epsilon as st and queries as the degree. Then you see that the same behavior is recovered. All right. Now I'm gonna spend one slide analyzing this polynomial. And okay, let's say I'm going to set my degree to be as large as possible. So which, if I take degree to be the effective norm t times the boundary, I will get that st is also t times the boundary. And then I check the condition dt is less than t times st, because these two are basically the same. This condition is satisfied even for t equal to 1, or actually some constant. It won't be 1, but 20 or 30. And then when I plug it into the upper bound that I mentioned to you earlier, then I get an area law behavior. So it recovers this line of argument, which is a variation on Chebyshev. It recovers the area law behavior for the commuting case. And all it shows is that this line of argument, which uses polynomial approximations, it's the right way, even all the way for commuting Hamiltonians. All right. But there's an issue with this construction for going to the general case, which is that the construction heavily relies on the integer spectrum of the Hamiltonian or of the function. That means only if you want to approximate integer spectrums, or not just in integer, it could also be a small number of points which you're interested in approximating. Only then you get a guarantee of this kind. And then the issue is that how do you generalize this to the continuous spectrum that is available for the non-commuting Hamiltonians? And that's what we'll tackle in the coming section, and we'll see how to get around the issues of continuous spectrum. All right, so another pause here. Any questions? All right. So let me explain how can you deal with the issue of non-commuting spectrum. So we'll do this in two ways. First of all, we'll make the improved Chebyshev polynomial approximation more friendly for the non-commuting case. And for this, we'll require the technology of robust polynomials. I will explain this in the next slide. And we'll use it, and we'll also have to deal with non-commutativity, and we'll then get an improved approximation in 2D. And this step will require the local gap assumption. So the first step will just be a rederivation of these polynomials of Kahn, Linear, Samirsky, and Burman, Cleve, Debol, Zalka, using a different method, which is via the robust polynomials. And then we'll proceed from there to doing the volume law behavior for the Hamiltonian case. All right. So let me explain what these robust polynomials are. Consider any Boolean function p, which takes m bits and outputs a bit. And let's say the degree of this function is D. Sherstov showed that there is a robust polynomial, which I'm going to denote by rho subscript p, where p is the function. Now, what it does is that it takes real number input, that means it takes any real number, m real numbers, and outputs a real number. And the degree of this polynomial is twice d, and it has the following robust properties. So take any binary string x coming from 0, 1 to m, and let's say you corrupt the values of these x by some real number. Let's say you, instead of x, you are looking at x plus epsilon 1 and so on, which is a real parameter. And think of epsilon as some small constant like -1 or 10 to 1. Now, if you feed this corrupted input to the robust polynomial itself, and rho p, it turns out that this polynomial stays very close to the original value at x1 to xn, up to this tiny error of 2 to the power minus the degree. So, so as you notice here that whatever corruption you do to these values xi, you stay close to the original polynomial. And we just wish that all the political systems were like this, but that doesn't really happen, unfortunately. So it stays close to the uncorrupted value. And what's interesting about this polynomial construction is that as the degree increases, you get a better and better approximation. So notice that the approximation gets better with the degree. Higher the d is better you are. Actually, the construction is quite intuitive for the special case of AND function, which I will use in the coming slides, but unfortunately, I won't have time to discuss that. But this is roughly what happens for the robust polynomial. Let me mention that this was inspired by some questions in quantum query complexity about composing bounded error quantum algorithms. Sorry. So Sherstov was inspired by some results involving Ronald and Harry as well for the motivation for these polynomials. All right. So I'm going to spare 2 red slides explaining how do you get the improved Chebyshev approximation using the robust polynomials. Now, I'm going to do it for the AND function, of course, because Chebyshev polynomials approximate the AND function, as I mentioned, via symmetrization. So for the convenience of later presentation, I'm going to consider these black dots, which are independent variables or independent variables which are going to be input into this AND, but I'll arrange them in this funny fashion just to make things compatible for the discussion on local Hamiltonian in 2D. But you don't have to arrange them in this strange 2D way. So think of these t times the boundary A number of variables, which are arranged like this, and divide them into several blocks, p over m blocks. And each block has m times the boundary A number of variables here. Now the AND on all these variables is same as taking AND on these blocks, taking t over m of them, and taking them all together and feeding into an AND of all these guys. It's just a simple composition of AND. Now what I can do is that, now my plan is to construct an approximation for this big AND. I'll do it in 2 steps. First, I will approximate all these inner ANDs, which is the function inside, by a Chebyshev polynomial Q with a constant error. And the degree will be square root of the number of bits inside, number of variables inside, that's m times the boundary of A. That's the number of variables. So I do this approximation. And then I will get the full polynomial for this AND function by using the robust function of Sherstov. That means I will take the Q, take the m copies of Q, I will feed them inside the robust AND on t over m variables, and this will be my polynomial for this AND function. So on the next red slide, let's analyze the behavior of this polynomial. So let's look at what is the degree. So degree is, as I mentioned, the robust polynomial degree is at most twice the degree of the original function. So in this case, AND had degree t over m, so the robust polynomial is degree 2t over m, times each of these inner polynomial q has degree root over m times the boundary. So that's what you get, and let's just evaluate it this way. Now, what is the error in this approximation? If you recall from the previous slide, the robust polynomial approximates by the error of 2 to the minus d, the original function. So through this step, you see that this AND function gets approximated by an error of 2 to the power minus t over m, where t over m is precisely the number of ANDs or the degree of the outer polynomial. So now let's do a 2-minute analysis of this. Notice that my m was a free parameter. I could have chosen anywhere between 1 to at most t. So I solve this equation. I get that m has this dependence. M is 4t square boundary by dt square and so on. And we plug m inside this, and we find that st is basically what was reproduced via the improved Chebyshev. Now, since m scales between 1 to at most t, we also recover the constraint that the degree has to be at least this and at most this. So all the properties of the improved approximation get recovered here. Okay. So sorry for 2 technical slides. Any questions about this?
Yeah, Anurag, just to make sure. So what did you lose here? So in the end, you construct a polynomial that's strictly a better approximation than the Chebyshev for the high degree range, or is there something that...
For the high degree range, yes. As the degree is larger than square root of the effective norm, or t times the boundary, if the degree is larger than root of the number of variables, then you get a better approximation than Chebyshev.
So you didn't lose anywhere. It really is, you get the same bounds as this, the one that worked only at integer points.
Yes, same bounds, essentially the same bounds. But this discussion was only for, so sorry, maybe I didn't mention it clearly. It was only for the classical case again. Like I was rederiving the classical case.
Wait, sorry, why for the classical case?
Because notice that this and composition gives you and only in the classical case. Like if these are the ground spaces of these variables for sure, but composing them like this gives you the full ground space only in the classical case. I'll come to this point later. So this construction is only for bits like the simple standard AND function. But I've just shown it in this manner.
Oh, I see. So as a, I see.
Yeah,
I see. So it's something a bit strange as a okay.
Yeah, I hope it's clear. I mean, it's just that just rederiving the same polynomial in this picture so that I'll use it later for the quantum case. But it's very simple. Just divide them into small parts and then approximate each part.
Right. So, but it's not exactly clear what this thing does at non-integer values. So
right. Yeah.
Computes this and thing, which for non-integer values is some.
Yes. So I'll address that in the coming slide. Yeah.
Okay. Thanks.
Indeed. Yeah. So that's a very good point. Yeah. So let's see what part of this construction works for the quantum case now. So let's bring back our local Hamiltonians. These are sitting here, and let's try to get things work. So recall the same picture as here. I divide this into these regions. These are these same regions. I'll come to these red things later. So notice that if you assume the local gap, that means this blue blocks have a local gap in their own region, then you can use the Chebyshev construction of the Hamiltonian here to go through the first step, the second bullet point, essentially. So that works out. That means that approximating the ground space of this m times the boundary a number of qubits by Chebyshev polynomial goes through. Turns out the robust polynomial is also quantum friendly. You can feed into it some quantum variables. It's totally fine. But the thing is that when you take these blue ground spaces and you combine them just by taking blue ground spaces, you don't get the full ground space. You're totally missing out the Hamiltonian terms that are living on the boundary. And this thing is not the ground space of the full Hamiltonian at all. Unlike in the classical case, where I just composed these together and I got the and or the ground space of all these variables in some sense. View and is out. So we have to make this work. We have to take care of the fact that these red Hamiltonians are also excited and they need to be satisfied. So what we can do is that, yeah, exactly. We're missing out the ground space of H in this process. So what we'll do, and this probably answers, hopefully it answers Thomas' question. And what we're going to do is that we are going to use the coarse-grained detectability lemma, which is a byproduct of detectability lemma itself. I won't describe in details what that does, but in our context, we will take these blue things, blue projectors, we'll take a parallel layer of these red projectors to cover these excited or unsatisfied Hamiltonians on these regions. And if I just take an AND of these guys or a product of these guys, the coarse-grained retrieval lemma guarantees that I get e to the power minus m close to the ground space on all the qubits, and where m is the parameter that I choose here. Now, what does it tell me is that I can repeat the same analysis that I showed you for on these slides, but with this additional error of e to the power minus m, which comes from the retrieval lemma. I can run through that. I won't go into those details. I hope you can trust me that I did the maths properly. And we obtain the result that under the local gap assumption, which I assumed for this quantum-friendly step of approximating these operators by local gap. Under the local gap assumption, the entropy scales as the boundary to the power 5 or 3. So we recover some aspect of this improved Chebyshev polynomial. And so that's one result. And you can ask, how far can this line of argument go? So it turns out that just hypothetically, let's imagine that I keep getting the improved Chebyshev approximation, which was precisely what I mentioned earlier. But I'll always lose this factor of e to the power minus t because of the dilemma. And a rough back of the envelope calculation tells us that if this kind of argument were working out, then this would give a subordinate law of boundary to the power 3 over 3, which is a work in progress, trying to figure this part out. So effectively, what's happening is that we're trying to construct these improved Chebyshev polynomials using additional structure of the Hamiltonian, for instance, the local gap, and the fact that these Hamiltonians are widespread, or kind of local. Sorry. All right. Any questions at this stage? Now I'm closing into the discussion section. Okay. So let me spend 2 slides on the local gap assumption, which I made in the previous slide. This assumption was also appears in prior works, for example, of Michaelakis and Zolak from 2011, and of Satat and Gillian in 2016 on quantum Loas local lemma. So the question is pretty clear that can we get rid of the local gap assumption? Is it known that we can get rid of it? So question is, if the spectral gap is constant, then is local gap a constant too? For this problem, let's look at a helpful example, which I borrowed from this work. Consider the following Hamiltonian, which is essentially classical. So this Hamiltonian acts on n particles, and the first 2 terms of the Hamiltonian, they penalize all those basis states in which the adjacent bits are the same. So they don't want 0, 0 or 1, 1 configuration. So for example, 0, 1, 0, 1, 0, 1 or 1, 0, 1, 0, 1, 0 would be fine. But then you add another term. For example, this is a very tiny term of 1 over n, and it only acts for even I. And then you penalize whenever you see a 0, 1. For example, if there was a 0, 1 here, then you would penalize it. You see that for this Hamiltonian, this is a ground state because there are no consecutive zeros and no consecutive ones. And this satisfies this term as well, simply because this only asks that for even places, even in odd places, there should be no 0, 1. So there's a 1, 0 here and 1, 0 here. So we're all right. But for example, the 1, 0, 1, 0, 1, 0 would not be the ground state of this, and its energy would be 2 over 3, which means that the gap of this Hamiltonian is 2 over 3. But if you look at just the locations I equal to 2 and I equal to 3, the local gap is very small. It's 1 over 3n. So does it mean that this is not true? Well, it turns out that if you do a simple normalization of the Hamiltonian, which I already mentioned in the very beginning, that we'll assume this should be the case. And if you rescale all these local terms to the span of the terms, then the new Hamiltonian even has a constant local gap, and you don't run into this issue. So the problem can be rephrased as asking that, is it true that for every frustration-free Hamiltonian, is there a transformation of the kind in the previous slide that takes you to an H prime, which is a sum of the projectors, such that the local gap or gap on small regions is at least the original gap to the power some constant? If that were true, then we could say that our result also holds without the local gap. So we don't know about this. Personally, I'm not aware whether the constructions on undecidability of spectral gap are counterexamples for this kind of transformation. If someone in the audience is aware, then that would be great to clarify here. Also, one aspect of this is that it is known that the gap itself can be lower bounded in terms of local gap due to Canabi's theorem and its generalizations. So if something like the first bullet point were really true, it would be quite interesting because it would show that the local gap and the gap are related by a polynomial factor, and that would, in some sense, it might show, for example, that for this family of sum of projectors, gap is decidable. So anyway, so again, I'm not much aware of what may happen in this direction. Let me mention, talk about the representation of the 2D ground state. So a recent work of Nilin Abrahamson, it shows, as a follow-up to our work, it shows that you get sub-exponential algorithms for preparing the locally gapped ground states of frustration-free systems. This work uses many of the tools that were developed by Arad, Landau, Vidic, and Bezrani, which I mentioned in one of the early slides. So one question is that, is it possible to, so this work gave a PEPS representation or some tensor network representation for the ground state. One question is whether you could improve it further if you just wanted the existence of a PEPS. And in particular, can AGSPs go around the issue which was pointed out in the work of Yimin Gay and Jens Isert, which is that error law doesn't really imply PEPS with polynomial dimension, but can AGSPs circumvent that? So that's an exciting problem to think about. One coincidence that I would like to end the slides with is that if you, as I mentioned, I assumed the gap or the local gap in our case to be a constant everywhere. So prior works had a scaling of boundary square by gap, even if under the assumption of local gap, they got the same number. Our result, it shows that we get 5 over 3 by 5 over 6, and the hope would be to get 3 over 2 by 3 over 4. As you notice, there's an invariance being maintained here. That is, this factor of boundary square by gap gets a simultaneous improvement. And if you look into the conjecture of Gosset and Huang, that the 1D scaling should be 1 over root gap because of the correlation length intuition, it suggests that resolving this conjecture might be important for obtaining an area lottery into 2-dimensional higher dimensions. So that's about it. With that, I will end the slide. Thanks for listening. Maybe I'll do a stop there. Thank you.
Thanks. So we have time for questions.
Mm-hmm.
Maybe while people think about their questions, let me just ask the question that you asked about the undecidability result. Is that because, well, I remembered, I hope someone will correct me, is that they gave a family of translation invariant Hamiltonians in 2D, I guess, even in 1D after a while, such that the spectral gap remains small for a while, and then suddenly ups. So
right.
In what sense is that okay, including in 1D, I think. In what sense is that not a counterexample, or why did you put it as a question? Just because
because like, is it possible to transform that Hamiltonian into a sum of projectors so that this behavior goes away? That's the question. I mean, I'm just not.
They don't use projectors.
Oh no. I mean.
Oh, okay.
Not right away, but that's what I'm wondering as well. I mean, I haven't figured it out myself. Maybe I should look closely at the paper and then maybe something comes up. But someone would just tell us as well. Yeah.
Umesh, I think you're still muted.
Yeah, hi Anurag. So I should say that I'm a great fan of your result. It's really fantastic. So let me ask you. You said something about boundary to the 1.5 as being the aspirational result. So can you say a little more about that and how you might move towards that, or why you think that's the right place?
Right. So as I mentioned, that if you do a heuristic analysis of the way this improved Chebyshev polynomial is behaving and the correction you get from predictive dilemma, you seem to be getting at that number, and it seems that some kind of a collection of observations, I guess, might help there. For instance, that you could analyze, you could use this construction over and over again and improve the results and so on. And those things might help to improve the bound. We are working on it. So once
And with respect to the local gap, you sort of said, well, one way you could approach it is by just saying maybe local gap is not that different from the gap itself. But have you tried more, going directly at the proof and saying, well, instead of showing that it's the same thing, maybe can you have you tried strengthening the proof in some ways?
We haven't given too much thought into whether we can remove the local gap assumption itself. Like there are some ideas around, for instance, maybe change the detectability lemma itself to try to get a better detectability lemma which does not require the local gap assumption.
Sorry, better detectability lemma that doesn't.
Yeah, a different kind of detectability lemma. Maybe this is an observation that Itai suggested, that maybe some variations on detectability lemma, because that's where the local gap comes in, because we're using the detectability lemma. So maybe there are variations on it. Yeah. But we haven't, in all honesty, I don't know, at least I haven't given too much thought into it, but maybe Itai and David have.
Okay, great. Very nice.
Oh, hi. Yeah, so it's a really nice talk. Can you comment on which sets A you can get the subvolume law for?
A collection of regular sets, for instance, a vertical one would be nice, rectangles, triangles. Effectively, the way you would see it is that you take your region and you try to move away from it parallelly outside and inside. And if your length of the perimeter doesn't change by too much, just changes by a constant, then you're good. Then you can prove theorems for those things. But if it's something very complicated, then maybe moving here and you don't want change to be too strong. Yeah.
But do you believe the result to be true for all sets, or is it only to be?
It depends on, I guess, applications. I'm not sure if physicists believe, or physicists even have calculated it for fractal-like shapes. I'm not sure about that, but yeah, I'm not aware of that. Sorry. Yeah, that's a good question.
Thanks.
Yeah, I mean, yeah, it might be true for every possible fractal-like thing, but fractals have too long a perimeter, unfortunately.
Did you say something about dimensions higher, by the way? Is that do you get?
Oh, no, I didn't. So one point is that if one obtains a subvolume law of boundary to the power 3/2, that's at the brink of getting a 3D subvolume law. I mean, any improvement would give you a 3D subvolume law too.
So currently there's nothing for dimensions higher than 2.
Yes. Yeah. So it's always, the theorem is always like a boundary to the power some constant, and now one has to look into isoperimetric inequality and see where it becomes true. But this improvement happens all the way. Yep.
Other questions? If there's no more questions, I'll slowly take us offline. So let me thank Anurag first for the great talk. Thanks a lot. Next week, we have Ronald de Wolf is going to talk about coupon collector problem, which is work that at least partially came out of the previous cluster that we had at assignments a summer and a half ago. So it'll be exciting to hear updates on that. And so if there's no more questions, I'll take us offline and see you all in a week. Hope everyone's doing well. Okay, I'll take it offline. I'll stop the recording. We can still chat if anyone wants to stay, ask questions off the recording.